Now we're going to move to the problem that we really want to answer, which is how can we just count general combinations? Combinations, say, of length k from an n-letter alphabet. Repetitions are allowed, and there's no condition that we have to have at least one of each letter. So this is just the fully general problem of counting combinations of length k from an n-letter alphabet. In order to answer this question, we're going to make use of standard problem 5, which we discussed in the last lecture. And we're going to do that by using that same trick that we used right at the end in the last lecture. Let's say we want to count combinations of length k from an n-letter alphabet. We can use standard problem 5 only if we know we have at least one of each of the n letters, but we may not have that. So maybe I didn't say this correctly. It's not going to be the exact same trick, but it's going to be a similar trick. So we're going to use the following trick. To our combination of length k, which might not have one of each letter, go ahead and add one of each letter. Just throw them in. Well, what happens when you do this? Then our combination has a lot more letters. It has k plus n letters. We started with k letters and we added n letters, one of each of the different letters that are available. But now what do we know about this new combination? It has to have at least one of each letter because we threw in one of each letter. Here's the important thing. I claim that if we count all the possible combinations of length k plus n from the n-letter alphabet, and we look at combinations of length k plus n that have at least one of each letter, I claim the number of those is the same as the number we were looking for, which is the number of combinations of length k from an n-letter alphabet with no conditions. There's a one-to-one correspondence between combinations of length k from an n-letter alphabet. I won't just always repeat that. That'll be general in this problem. A one-to-one correspondence between combinations of length k with no conditions and combinations of length n plus k with no missing letters. How does this one-to-one correspondence work? Well, just the way we described above. If you have a combination of length k, just add one of each letter and you'll get a combination of length n plus k with no missing letters. If you start with a combination of length n plus k with no missing letters, take away one of each letters and you're down to a combination of length k. This one-to-one correspondence shows that the two sets have the exact same size. And of course, our goal is to count this, the combinations of length k from the n-letter alphabet with no conditions. Using standard problem number 5, we can find the number of combinations of length n plus k with no missing letters, and that's just n plus k minus 1, choose n minus 1. So the number of combinations of length k, repetitions allowed, but no other conditions, is just the same thing, which is n plus k minus 1, choose n minus 1. And that brings us to standard problem number 6. How many combinations are there of length k from a set of size n, repetitions allowed, but no other conditions? The answer is n plus k minus 1, choose n minus 1. Or we can see that's actually the same thing as n plus k minus 1, choose k. Why? Because from what we've seen earlier, n plus k minus 1, choose n minus 1 is actually the same as n plus k minus 1, choose n plus k minus 1 minus n minus 1 which is exactly n plus k minus 1, choose k. And this is what we call n choose k with repetitions. We give this new name here for the number of combinations of length k from a set of size n, repetitions allowed, and we can evaluate that as n plus k minus 1, choose k. It's certainly fine to use n plus k minus 1, choose n minus 1, but often this will be simpler. Here's an example. Let's say we have a bunch of wooden tiles with letters on them. We're going to assume that we have as many as necessary. You want to put 10 tiles in a bag. You can use multiples of any one letter, as many as you want. Just somehow you have to have 10 tiles in the bag at the end. How many different ways can you do this? Well, we just have to count how many combinations are there of length 10 from an alphabet which has 26 letters. When I say letters, I mean standard English alphabet letters. So we want to count the number of ways you can get a combination of length 10 from a 26-letter alphabet, and by problem number 6, the answer is just 26, choose 10, with repetitions allowed. And that will be then 26 plus 10 minus 1, which is 35, choose 10. You could write this as 35, choose 25. That would be using this first formula, and that would certainly be correct as well. And if you need to know the number, you can write that in a number of ways. You can write that as 35 factorial over 10 factorial times 25 factorial, or you could write that as 35 times 34 times 33 times 32 times 31 times 30 times 29 times 28 times 27 times 26, dot product of 10 numbers, over 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. What if we wanted to do things differently? What if we wanted combinations of length 10? We wanted to put 10 tiles in the bag, but we couldn't repeat the letters. We could put at most one of any letter in the bag, so the 10 letters had to be different. How many ways can we do that? Well, that's back to an earlier problem about just combinations, how the combinations numbers are defined, and that answer would just be 26, choose 10. We just have to pick 10 of the 26 letters and put one of each of those corresponding tiles in the bag. So the answer is 26, choose 10. I'll leave you to write down what that equals.